All right. Let's go over the answer. All right, so here's my initial equation. We had hydrogen, H2, and we had fluorine, F2, becoming hydrogen fluoride. I put a 2 in front here so that way it balances that equation. Don't worry if you're like, I don't remember how to do that, because we will have a lesson on balancing equations. I want to grab my resource sheet. Find that. I'm sorry about the wind. I'm guessing it's better to be windy. All right, let's say I saw this and I'm like, I don't know what to do. I don't know how to break this apart. I don't remember my ions. So lots of different ways you can tackle it. Probably the easiest way is to take your resource sheet and look for things. So remember, you are going to get this on the assessment. So I see that I had hydrogen gas, and then I see H+. So what that probably tells me is that this guy here, if I was to break it up into its two pieces, would be 2H+, and now let's find the fluorine and the charge of that fluorine. Actually, I should say fluoride because it's the ion. And I don't think it's on there, which is useful. So, in the event that that's not on there, think about the periodic table and think about the groups and the trends and patterns. So, fluorines in group 17. I know atoms in group 17 have 7 electrons. We want to get to the octet rule to be stable. So, if it's gaining 1 electron is what we're looking at. So, group 17 has a -1 charge. Does that ring a bell a little bit? So, the fluoride is a -1. Are we good so far? The other way I can double check myself is, does it make sense when I put it back together to its ionic compound? So ionic compounds should have no charge on them. So since my hydrogen is +1 and my fluoride is -1, +1 plus -1 equals 0. So it adds up properly. Again, it's another way to idiot check myself. Are we good so far? Okay. So now that I've broken it apart into smaller pieces, what I'm going to do is I'm going to write my half equation. So this is my full equation. I want my half equation, because that tells me oxidation and reduction. So look at our hydrogen, look at our hydrogen. Again, write our arrow. H2, 2H+. That arrow is such a critical piece of information because it tells us reactants and products. Reactants is what we've mixed together on this side. Products is what's being produced. We good? All right. So when I'm looking at this guy, this is the element. There is no positive or negative written on the top, so it tells me it's an uncharged molecule. So with that uncharged molecule, that's my starting point. It's basically like 0. And when we talk about oxidation numbers, that oxidation number for this guy is going to be 0. We look at this guy over here, and I see that there's that positive symbol there. So it's positively charged. So we have something that has no charge and something that's now a positive charge. The way this has changed has to do with the gain and loss of electrons. What we need to remember is electrons are negative. So if something is going to a positive number, it has lost those electrons, lost those negative charges. So what that tells me is that it's going to be on the product side. So I have my electrons over there. And in fact, I have 2 of them because I have 2 hydrogen atoms. Are we okay with that so far? And it makes sense mathematically if I check. This is +1. I have 2 of them, so that's +2. This is -1. I have 2 of them, -2. +2 plus -2 equals 0. This guy's 0. We good? Yep. So, mathematically speaking, what we're checking, this is +1. We have 2 of them, so that's +2. Yeah? This is a -1 charge. I have 2 of them, that's -2. I add these 2 numbers together, I get 0. What's on this side? Also 0. Yeah? So this half reaction here is my oxidation reaction. We think Leo the lion says grr, because I don't like oil rig. Climate change, y'all. So, loss of electrons. I've lost my electrons. They're on my product side. We have lost them. So that's an oxidation reaction. Now, what's frustrating about the vocabulary is that, actually, no, I'll hold off on telling that one. We'll see the other equation next. All right, next half equation. We're taking our fluorine and we're taking our fluoride. So we're going from our H2 to our 2F minus. Yeah? Again, if we look at our charge, this has no charge. It is 0. This guy over here has a -1 charge. Yeah? And I notice that I have 2 fluorine atoms. So if I do 2 times -1, I get -2. How do I get negative numbers? I have to add electrons. And when we add electrons, we're adding them on the reactant side, because it's being added with the fluorine. So those two get added together. I then get my fluoride ion that's negative. So in this case, this is a gain. Again, Leo the lion says grr. Gain of electrons, reduction. Watch the charges because they tell us a lot. Now, let's talk about how we're going to idiot check ourselves. All right, arrows. I like to have them center in the page so that way I can easily line things up and cancel them out. I'm looking over here. I see I have electrons on my right-hand side. I also have electrons on my left-hand side. That's what I want, left and right, because then they cancel out. What's happening with these redox reactions is that this electron that's coming from the hydrogen is being given to the fluorine. We can't create or destroy matter. So the electrons need to come from somewhere and they need to go somewhere. So you should always have them on opposite sides of the equation. If they're on the same side, you've made a mistake. We good? And then this is where the vocabulary comes in with the weird switcheroo. So we call the hydrogen our reductant. And we call it our reductant because it is reducing the fluorine. We then call the fluorine the oxidant because it's oxidizing the hydrogen. I'm sorry that this is the way it is. Someone picked those vocabulary words and it just stuck. All right, questions, concerns, comments? None? Okay. What I want to point out to you guys, because I can see some of you guys still haven't mastered this, is on Google Classroom. Hopefully it loads. There we go. And we go to the level 3 chemistry class. And we go to the lesson that I posted for yesterday. I saw you guys? Or Wednesday? Yesterday? Okay. So this is yesterday's lesson. I always put all the information on there. It's also on the Google site. But if you click that link, you'll see on here that I have on our learning task. Actually, maybe I'll make it a little bit bigger. Is that I made that GIM kit, remember? So you guys, yesterday you played that GIM kit. You can click on that link and you can practice your identification of redox using that. So instead of playing the GIM kit game, you just practice the multi-choice questions and it kind of acts like a Kahoot basically. So I really highly recommend you do that so that way you can master our vocabulary. The other thing that's there on my Google Classroom is I have a scan of the notes from the other day. So if you were absent, I don't think anyone was, you can copy those down. And I've also recorded the lesson from yesterday as well. And in fact, I'm recording this one right now, so that will be posted with today's lesson, and I'll scan this on top of that. Cool? So I'll make the GIM kit bigger, and I'll put a little icon over here, so that way you guys can actually access it a little bit more obviously. But it's a great way to, like I said, practice that vocabulary and master it. A lot of the achieved requirements is just vocabulary, so we got to get that down. All right, cool. Let me go back to our lesson plan. All right, so for today's lesson, what I wanted to talk about was the basics of electrolytic cells. So if you guys remember our first lesson that we did for read off, we played vocab mystery, not vocab mystery, vocab detective, and we talked about two different types of cells. We talked about the electrolytic, and we talked about the galvanic. Unfortunately, with that lesson, the audio didn't record, so I don't have the video up. But don't worry, we are going to go through those terms again, so don't stress. So we're going to look at the basics, basically covering the achieved requirement for this half of the internal. So with that, our success criteria, we're looking at using the redox terms correctly, but we're also talking about electrodes. I have the define bolded because we're just talking about the basics of the electrolytic cells, and then we'll work on explaining what's going on. And the other thing that's really important for the standard is the observation. So looking and trying to see what's going on there and identifying what's what. Are we good? Cool. So let's do some practicals. Practicals. All right. So let me highlight that because that's what we're doing first. Spotlight it. Can we make that text bigger so you guys can actually see it? Bigger. There we go. All right. So what you guys are going to do in a moment is you are going to set up an electrolytic cell. With that electrolytic cell, what I want you guys to do is make some observations on the setup and also the chemical reaction that's occurring there. I don't want to tell you guys what it is, because I want you guys to see things and observe them and kind of just really see the nitty-gritty. So with the electrolytic cell, I have four, so they're going to be groups of three. We have a little power pack. So this power pack gets, I'm trying to think where's a good spot for me to stand. This power pack gets plugged into the electrical socket. We need an energy supply. I think we want the DC current for memory. The other thing you guys are going to need are beakers. I'll put those out too. We're going to need a beaker. We're going to need 2 wires. Two wires and 2 electrodes. Try to grab the ones that have the little metal bit on them. Alright. So when it comes to my setup, today, it's beaker, wires, and electrodes. These electrodes are made of carbon. If you rub it on a piece of paper, you'll notice that this is carbon. Alright. So, yeah, carbon. You can rub it on a piece of paper. Alright. We are plugging in our 2 electrodes into our power pack. We're going to use a little alligator clip to attach our electrode. Make sure you're touching the metal, because you know metal is conductive, plastic is not. Yeah, we have that positive and negative. If they're not connecting very well, I can get us some sandpaper and sort it out. All right, these 2 guys go into our beaker. So that's what it should look like. Yeah? With the electrolysis, we obviously need an ionic solution for that. So I have got us some copper sulfate. Once you guys have it set up, I will give you a little bit of copper sulfate. And I'll just pour it in, you don't need a whole lot. And then you'll be able to shut it off. Make sure you take your notebooks with you because I want you to write down observations about how you set up this cell, and then once you turn it on, what's happening with this copper sulfate. Okay? So goggles on, hair needs to be tied up, roll up your sleeves. Groups. You have 4 groups, ideally like 3 or 4. 4. And we'll have 1 group of 4. 2. Group of 3, really don't work together. Another group of 2, 4, 5. Okay. Alright. I will leave that up there as my setup. You guys make your own. Don't take my setup. I haven't actually tested it out, so I'm assuming it's going to work. Goggles on, hair tied up. I'm just going to quickly check that the setup actually works. That'd be awkward. You don't want to work next to here, that's fine. I totally understand because the wind's blowing real bad. Make sure this works. Otherwise, you guys are going to have not a fun time. Alrighty. Cool. So let's get started. So observations before we even put the copper sulfate in there. What are some things we noticed about the setup? How many beakers did we have? Just the one. So I'm going to draw 1 beaker. What else do we have? 2 rods. Yep, our electrodes. What else? We had copper sulfate. Yep, and it was blue. I'll talk about that in a moment. All right. What else? We had wires. What else about those wires? They were electrical wires. Did I plug it in? Yes. So I had direct current. Yeah? All right. So some things to note that we saw. We saw that we had a power supply. That's really important for us to remember because if you, in our first lesson with redox, we talked about how electrolytic cells need an energy supply. They are non-spontaneous. So that's showing that. So we have an energy supply. And that's because electrolytic cells actually, yeah, I like the cell better. It's energy supply. Electrolytic cells are non-spontaneous. So that means if it's non-spontaneous, I need energy, which is coming from this guy here. Are we good so far? Just making sure I have an image up so I can get everything that I want. That's the image I wanted. All right. So we noticed on, what did we notice on one of those electrodes? It started turning orange. So we saw, like, I'm going to actually use the orange color. So we saw one of those electrodes getting coated with orange, right? Yeah? So we know inside this solution here, we had copper sulfate, and that was aqueous, so it was dissolved, and that was a blue color. What causes that blue color? If we're not sure, we look at our resource sheet, which I have lost because of the word. Copper. So the blue is from the copper 2 ion. And it's aqueous as well. So what is this orange stuff that was forming? Not rust. Copper. So that's copper forming. Copper, the solid. So CuS. So, we good? And I like to write my observations. So copper solid, and we saw that it was kind of like a brown color. Brown, I would also accept orange. Pinkish brown. All right. So we need to figure out if this is an oxidation or reduction reaction, right? So we started with what in that solution? Copper, the ion, Cu2+. It became copper, the metal, S. It is a reduction. Very good. Yeah. Because you see how it's going from positive 2 to 0. So I've gained 2 electrons. So what was happening at this electrode here was my reduction reaction. Do you know what we call the special name of the electrode? No. Nah. So this here is my cathode. So the cathode has reduction. And it's always going to be that way. Did anybody have a look at the power supply to see if it was coming out of the positive or the negative? It was the negative. So this is the negative electrode. It was from the negative electrode. This electrode here is the negative electrode because you have a negative and a positive with all batteries or with all kind of electrical setups. So you have a negative and a positive. So this is the negative electrode. This negative electrode has the reduction reaction occurring. We figured that out because we saw the copper metal forming around it. And we know the copper ion is being reduced to form that metal. And then this here, because this is my reduction reaction, we call this electrode the cathode. The other way to remember it is cation. Yeah? Cathode, cation, and that is a cation as well because it's a positive ion. We good? All right. What was happening on the other side? Bubbles. Now we got to figure out what the bubbles are. Look at our resource sheet. What do you think the bubbles could be? Sulfate. Anything with the sulfate that we know that like makes a gas? Remember, this is aqueous, so what else is there?
Wait, hydrogen.
We could have collected it and we could test it to see if it was hydrogen. So we have water is our other option, right? There's water in there as well. So we're not sure if this is hydrogen or this is oxygen right now, because those are the potential options when we split up water, right? I will tell you that it is oxygen. I won't go into depth as to why it is oxygen. And in fact, this kind of reaction, this is a more complicated one. I'll show you guys a simpler one to do. But I just want to get you guys kind of looking at that kind of stuff. So we had on this side, my oxygen's coming off. If we're thinking about water, I'm trying to think what's the best way. Oh. Trying to decide. H2O going to O2. Now, unfortunately, with this, we have to look a little bit at oxidation rules. I'll do a whole lesson on oxidation rules later. You're just going to have to trust me right now, okay? So I will tell you, this oxygen here has a charge of -2. We're going to the element, so what should that be? 0. So what's happened? It's unbalanced, so what has happened to the electrons?
Lost.
It's lost. So 2 electrons on that side. Does that match up when I look at this equation here? I have one on my one on my reactant side, one on my product side. So what that tells me is these 2 electrons that were lost here have gone over here. Mena, do you see it? So if I've lost electrons, what do I have? Oxidation. Did you guys notice what charge that electrode was? Positive. Gotta have one positive, one negative. And we call the we call the electrode where oxidation is occurring the anode. The way I like to remember it is anode starts with a vowel, oxidation starts with a vowel. Reduction starts with a consonant, and cathode starts with a consonant. So you're just matching vowels. So anode, oxidation, cathode, reduction. So now I've got my 2 path equations. We're also making our observations. We see bubbles, and it's colorless. Yeah? Are we okay with that so far? So that's the reaction we saw. Questions, concerns, comments? Keep going? All right. This one's actually more complicated than what you guys will be doing on the assessment. Just FYI. On the assessment, what I will give you are things that are, instead of aqueous, liquid. So we don't have the water component to it. That's going to make your life a whole lot easier. So another example. So here's another setup example, and this time I'm going to do copper chloride. It is going to be a blue solution as well, because copper ion. And here we're going to have, what do I say? Cu2 plus and Cl minus, because that's how I break up the ion. Now, the thing to remember about electrolytic cells is that we're always going from the ions back to the element. So we're going from the charged to the uncharged. The other thing in this case is that we are doing liquid, and since we're doing liquid, I don't have water. So I've melted the copper chloride. Why do I need to melt it or have it dissolved? Why can't I just use normal salt? Won't have the same effect? Think about structure and bonding. It's not the metal. Has to do with structure and bonding. Why do I need my salt to be either dissolved or molten in the liquid state? Why can't I not use solid salt in this? I need the ions to be mobile. They need to be able to move around. They can't move around when they're stuck in the 3D lattice. It's positive, negative, positive, negative. Okay? So to simplify this, we just have liquid, we just have the ions, we don't worry about the water. Again, we label cathode and anode. At the cathode, we have the reduction. I look at those ions. I want to go back to element. So if I was going from copper 2 to copper, we already know that that's the reduction reaction because we did that one before. Do we agree with me? And this is reduction. All right, with my chlorine, so I should say chloride, I'm going to chlorine gas. Agreed? All right, I'm negative to 0, so what's happened? Bye-bye electrons, see you later. Electrons are on that side. I've lost electrons, so that is oxidation. All right, I'm just gonna tidy this up a bit so I can show you guys what the achieved requirements are. But basically what I'm looking for the achieved, you will get the picture set up for you, but you have to label it. So what I'm looking for is, have you labeled cathode and anode? Have you labeled that this cathode is the reduction reaction and the anode is the oxidation reaction? The other thing I'm looking for is, do you know your reactants and your products? So knowing that you're starting with copper as the ion and chloride as your ion. Then stating the products to that. So chloride's becoming chlorine gas. Again, you use your resource sheet to find them. Copper is becoming the copper metal. So I need you to identify products and reactants. And the last thing I need for the achieved is to state what reduction and oxidation mean. Reduction, loss, electrons, oxidation, gain. Sorry, nope, loss. Got it the wrong way around. So for the achieved, that's all I need. The hardest part is going to be basically taking the ions to the elements, I think. A lot of people get them the wrong way around. I don't even need the electrons there. I don't need the equations balanced. That's getting up to the merit level now. So I'll actually put that into blue. So stuff like this, balancing my equation, that's the merit level stuff. The achieved, I just need to know product and reactant. All right, I just got my 5-minute warning. Do you guys want to break or do you want to keep working? Keep working and bank the time? Okay. Can I move this? All right, I will scan it. I will put it online. All right, so move that out of the way. Move this to be our highlighted thing. All right, so make it a little bit bigger. There you go. All right, so I have given you guys a list of 8 different ionic compounds. All of these ionic compounds are liquid, so they're in the molten state, so you don't have to worry about any water. On some refill, you can write up basically what I have here with our cells, and I just want you to write things up to the achieved level. So identifying which one's which, that sort of stuff. It'd also be good if you guys stick in some observations. I gotta double check the success criteria to see if you need the observations for the achieved. I can't quite remember off the top of my head, but I'll double check it. So lots and lots of practice with it. Use the resource sheet to help you figure out what's going on. I think that's mostly all I have to say about that. This is your homework. It's going to be due on Thursday, and my plan is for Thursday to give you guys the first half of this assessment to the achieved level. All right, I haven't talked about any of the merit or excellence stuff, so don't worry about that yet, because we got to talk about oxidation numbers and balancing equations and stuff like that. So I'm holding off on that because I want to make sure you guys have the safety net of the credits first. Now remember, this is only half of the assessment. Okay, this is on Google Classroom. I see people madly copying it down. It is on there. And feel free to snap a photograph of it, but just work your way through it and practice it. Okay? I think that's all I have to say. Oh, Monday's lesson, I will give you guys the whole, like as a study period. Okay? So don't stress too much, but do start studying now. Okay? What questions do you have? All right, nothing? Go ahead and go. Let me double check the assessment criteria about the observations. The observations, I just double checked it, are merit, so you don't have to worry about doing that. So you can just write down the identifications of reactants and products.
And then choices?
I'll do the chief stuff first. Don't worry about the excellence yet. The other thing you need to write down, no, we will do the excellence. I'm just not doing it today. All right, the other thing you need to write down, this is a non-spontaneous reaction.
Is that for like everything?
That's for achieved. Or you can write down that it needs energy. So everything I've written in red is the achieved. The stuff that I've started adding in blue, that's getting us up to merit. Because I wanted just to show it to you guys so you can help kind of figure out oxidation or reduction. Cool? Like I said, we'll practice this some more on Monday. But the list is on Google Classroom. Go ahead and start practicing it. So that way when you show up on Monday, I can start marking some of your stuff and give you feedback. Yeah? Is there 10 minutes? Is it 50 that we end? Or 40? Damn. Yeah, we're done.